So the other day, like on any other day, I was sitting at my desk and I was looking at my lamp and I was thinking of our understanding of light, like you do. And I thought about how my understanding of light changed. In high school, I was taught that light was made up of electromagnetic waves and how those waves could have different wavelengths and frequencies, and that's what changed the colors of light. Right? That is basically my high school understanding of light. But I've come to learn over the years that light is more complex than that. I've learned of wave-particle duality, and that the discovery of that is one of the main reasons for the birth of quantum mechanics. And I find that really interesting, so that's what I'll be talking about today.
Let's just jump into this, guys.
In 1665, the Italian physicist Francesco Grimaldi published his discovery of light diffraction and pointed out it resembled the behavior of waves. Now, a year later, Sir Isaac Newton published his experiment on how light behaved like a particle. He thought light must be a particle because he thought that the geometric nature of reflection and refraction couldn't be explained by waves, as they don't tend to travel in straight lines. So he conducted a crucial experiment on diffraction of light. The wave theory said that light waves were made of white light, and that the colour spectrum we can see when passing light through a prism was the corruption of light due to it being through the glass. Sir Isaac Newton disproved this theory as he passed light through two prisms, where light was split in one and recomposed in the other prism. If the wave theory was correct, then if the light was passing through the prism, it would be corrupted no matter how you place the prisms, so it would come out with a different colour. However, it didn't, it came out white. So Newton thought that this proved the light was a particle, but many were still skeptical because Newton claimed that diffraction was another type of refraction. However, we now know that's not true. Diffraction is the bending of waves around obstacles and openings, while refraction is the change in direction of waves that occurs when waves travel from one medium to another. At the beginning of the 19th century, Thomas Young conducted his famous double-slit experiment, where he pointed a laser at a double slit and he got an interference pattern, much like one you would get if you put sound waves or water waves through a double slit. Right? Which proved light is a wave, because particles don't interfere the same way. The way that waves interfere is they can interfere constructively or deconstructively. Constructive interference is when two waves meet peak to peak, so at the two highest points, and they come together to form one bigger wave with a higher amplitude and transfer more energy at that point. And destructive interference happens when waves meet peak to troughs, and the two waves cancel each other out, leaving no energy being transferred at that point. So as light goes through the double slit, it diffracts, and it can only diffract if the slits are small enough. As they diffract, they interfere with each other, and that proves light is a wave, because particles don't diffract, right? Or do they?
No! Anyway.
He also proved that light is a transverse wave, which is a wave that oscillates perpendicular to the direction of energy transfer, i.e. where the wave is actually going. So the wave will, wave up and down. Wait
a minute!
The wave will wave up and down. Excellent explanation.
Sometimes my genius it's almost frightening.
So the actual wave, the energy transferred, is going to move forward, but it will oscillate up and down. Right, an example is a string a slinky is good because you can look at both the waves with it. If you shake it up and down, like if someone else is holding it and you're shaking it up and down, that's a transverse wave. But if you're just squishing it, that's a longitudinal wave. And what's a longitudinal wave? A longitudinal wave is a wave that oscillates in the same direction as the energy transfer, so it's basically just squishing. A good example is sound. Sound is a longitudinal wave. But how do we know light is a transverse wave? Well, we know that because of polarization. What's polarization? Well, let's take a look at an electromagnetic wave. An electromagnetic wave is basically the disturbances in the electric and magnetic fields, which are perpendicular to each other and the direction of the wave. The reason there's both the electric and magnetic field is that if there's a disturbance in the magnetic field, that induces a disturbance in the electric field. Right, we're going to talk about that a bit more in a minute, but they're at right angles to each other. Right, let's take a look at this. This is unpolarized light. The disturbances are in all directions. We're only looking at the electric field for the sake of simplicity of the diagram, because otherwise it would be just all over the place, but the magnetic field is implied, right? So imagine we put a filter on top of it, right? And only the waves that are in the same direction as the filter can pass. The result is we have plane polarized light, so it's polarized into one plane, like up and down. If we put another filter on top of that, at right angle to the last filter, no light can get through. This is polarization, and this only works if light is transverse. But how do we know light is electromagnetic? Because I said that that works for electromagnetic disturbances, right? Well, we know because of Maxwell and his famous 4 equations of electromagnetism. I was going to explain them fully in here, but I started making the notes and I realized how long that would take, so I won't. Instead, I'm going to link in the description a video that I picked out specifically so that, well, a series of videos actually, but I'll link it in the description, and I've picked it out so it's for beginners. Like, it's not just for beginners, but like, if you're a beginner, you will understand. Just please watch my video first. Okay, I've worked really hard on it. Please watch my video and then watch that. I'll summarize the things.
Genius.
I'll summarize the equations here so you can know what's going on, and then if you want to know about them in more detail, you can go watch that. The first one, it says the EMF, which is the electromotive force, which if you don't know, you can for now just think of it as the potential difference or the voltage. They are different, and I'll link a video on that as well if you want to know about that. But that's a good enough thing for now. It says the EMF across a loop of wire is equal to the rate of change of the magnetic flux through the wire. So that says when you change the magnetic field, you induce an electric field. Right? You probably did an experiment in high school where you put a bar magnet through like a loop of wire, and then you got a current going through. I know I did that. So that's what that says basically. Now the second one, basically the same thing, just the other way around. It says that as you change the electric field, you get a magnetic field. Right? Think of electromagnets, how you put a metal and then you surround it in wires and then you run a current through those wires. I'm pretty sure most people did this in high school as well. And then you get an electromagnet. Right? The other two, they're not as important for this video, but I'm gonna say them anyway. The third one, this one just says how electric fields behave, how they propagate. And the fourth one says there are no magnetic monopoles, i.e. on magnets there'll always be a south and a north pole. I mean, maybe not. There might not be. People are looking for magnetic monopoles and that's a whole thing. I'm not going to talk about it now, but maybe not, you know? So those explanations were very oversimplified, but, you know, they're good enough for now. And Maxwell did a bunch of calculus magic, and he figured out that his equations apply to light, right? And he could calculate the speed of light with them. So now we know that light is electromagnetic waves. I don't really understand how he derived it because it's quite high-level maths, but I'm working on it. But I'm sure you will find someone who can explain that if you're interested in that. Right, so that's going to be the end of this video. There's more I want to talk about, but I'm going to make a part 2 because this video is taking too long to edit already. In the next one, I'm going to talk about the photoelectric effect and the ultraviolet catastrophe and other things. Basically quantum mechanics, right? This one was a bit... well, I don't want to say boring, but, you know, the next one's going to be more exciting, right? So I hope you come and watch that one, because that one's the one I'm excited about. But thank you for watching this one, and thank you for all the nice comments, and for the people who liked and subscribed and all of that on the last video. That was really nice. I wasn't expecting that. I thought like maybe 1 or 2 people would show up, but it's great that more people, and that you seem to like actually like it, which was great. I didn't use a script today, and I tried to make myself a bit louder because some people said I was a bit quiet. And I'm not using a script today because I've been told I sound a bit monotone when I'm reading, so I tried not to do that. And you know, it's a bit less structured, but I hope it was alright. I think I sound better this time. I think this one is a bit better. Well, tell me what you think. If you didn't like something, then tell me. If you liked something, then tell me. And I will, you know, react accordingly. Alright, thank you for watching,